Okay, good morning, everyone. Thanks for tuning in. Today, we're very excited to have Professor Cardoso, world expert in applying general relativity to experimental situations. And he's going to tell us about testing general relativity with gravitational waves. Please take it away.
Thank you, Dan. It's really great to be here. I know it's also a commonplace to say these are great times to be doing gravitational physics, but it truly is correct. And it's good to maybe start by reminding ourselves that it's been more than 100 years since what I would say the first observational test of general relativity was done. This was the light deflection that Addenda saw in his 1919 expedition. I always like to dig up historical notes, and this is something I did a few years back, going back to the New York Times at the time, and you see here a series of 3 news, roughly separated by a week or so. And you see the first news. This was November 10, 1919, when news came out of the result of the expedition, saying that men of science are more or less agog over the results of eclipse. Einstein's theory triumphs. Stars were not where they seemed to be, or were calculated to be. You don't need to worry. And then a week later, and this is the thing that I like the most, you don't need to worry, because we agree that the theory can be disregarded for all practical purposes. Newton's law is safe. Well, in fact, I want to talk about Newton's law not being safe, but also about the fact that at the same time, in fact, a few years before this, the first exact solution, non-trivial solution of the field equations that really describe strong gravity regions where Newton's law is not okay, was discovered by Schwarzschild. This is also, now we understand, the first black hole solution. At the time, this was a non-spinning solution. Simultaneously, by the way, Jan Droste discovered exactly the same solution, a vacuum, spherically symmetric solution, asymptotically flat to the field equations. But unfortunately, his advisor was traveling and he did not publish the results on time. So the Schwarzschild solution is how it came to us. Now we can generalize this. We understand now how to generalize the solution to include spin. And this is the most general solution of the vacuum field equations that describe a black hole. And I'll be talking about black holes for all of my talk. And there's 2 reasons for this. The first reason, of course, is the unique property of black hole solutions in general relativity that connects to their uniqueness. And the statement is that any asymptotically flat vacuum black hole solution must belong to the Kerr family that I wrote down here in units where the speed of light is 1 and Newton's constant is 1. And you see that there's 2 parameters here, the angular momentum A and the mass m of your spacetime. And this, of course, only describes a black hole, so it only has an event horizon if the object doesn't spin too fast. So if this parameter A is smaller than m. And it's always important to stare at this, I think, solution for a few seconds to realize how extraordinary it is. And I like to cite Chandrasekhar with respect to this, that really is the most shattering experience to realize that all of the black hole solutions, all of the black holes in the universe belong to this family. This provides an absolutely exact representation of an untold number of black holes in the universe. It's really amazing. And it makes, the quest to use black holes a very simple one, because they're really simple objects. But the second property connects to the fact that we expect new physics around black holes. And the reason is tied to the singularity results by Penrose and others that states that whenever you form a trapped surface, then something is going wrong in your space-time or with your theory. I wrote down the consequences of having a trapped surface formation. Either you have negative energy, or the field equations are violated, or even the very meaning of a space-time manifold goes away. Okay, so that means that black holes are simple, but their interior is also the very failure of the theory they come from, right? And so there's several ways where new physics can come from. Either you totally stop gravitational collapse from forming horizons, or then the resolution of the singularity turns out to change the near horizon physics of your black hole. So it's really important to go out there and test strong field regions where you think black holes might arise. Now, Penrose also put forward a conjecture to more or less save the day. This comes under the form of the cosmic censorship conjecture, that either no singularity is visible from future null infinity, or then that general relativity is a deterministic theory. Okay, I'm not going into detail, but these are just conjectures. And in fact, we know of examples where it breaks down. So it makes a lot of sense to go out there and test this. Let me also add that in one of the papers where singularities are expounded upon by Penrose, he also deals with energy extraction from black holes. In particular, he looks at the region called the ergoregion, the static limit, where things cannot remain at rest. And he shows that because of this, you can build devices that extract rotational energy away from spinning black holes. The idea is really simple, right? You build this device, for example, you take a metal ring, you lower it into this ergoregion. It cannot remain at rest, so it has to co-rotate with a black hole. So you attach a couple of metal shafts to a magnet. The magnet needs to spin, and therefore it needs to induce a current in these coils. Okay, it's a very naive idea to show that you must be able to extract energy away from spinning black holes. It's not a crazy idea, because you can do this with stars or anything that spins on Earth. Okay, the difference is that we're talking about vacuum. You're extracting energy away from pure vacuum. And I'm going to come back to this mechanism in a few slides. Very good. Now, isolated single black holes are very simple, and they hide some failure on theory. But when you place them in binaries, another magical kind of property shows up. Black hole binaries are also special systems in our universe. Okay, and I think there's several reasons why this is so. One of them, for example, is that if you try to polarize one black hole with another, you'll realize that the tidal of numbers of black holes vanish in general relativity. Okay, it doesn't alter the multipolar structure of a black hole if you place the companion around it, so to speak. But also, if you place the system initially with some arbitrary eccentricity and you let it evolve, gravitational wave emission will tend to very quickly circularize the orbits. I'll show you one example in these panels below. So you start with eccentricity on the y-axis and the semi-major axis on the x-axis. I'm placing the binary within some environment with some density, okay? And you realize that initially the environment, it exerts a gravitational pull that we call dynamical friction on each of these guys. So the eccentricity tends to increase, but then at some point, gravitational wave emission dominates over the process and eccentricity decreases very quickly. So by the time that these objects merge, you basically have a system in a quasi-circular trajectory, evolving slowly under radiation reaction. It's a very neat, very simple system to do physics with. So now that we know we can observe black holes in the electromagnetic spectrum, but especially also in the gravitational wave band, there's a series of questions you can try and answer that you should try to answer. The first is, well, is it a black hole at all? How do we know? How do we provide evidence that we have horizons? How do we even quantify the statement? And is it a Kerr black hole? Does it belong to that two-parameter family of spacetimes? And if not, can we constrain modifications to GR? How do we do this? How do we go around and constrain alternatives? And once we are confident that we are dealing with black holes, and because they're really simple, can we use them as tools, as laboratories, to understand either new degrees of freedom or the environment where they evolve? How do we do this? Now, I'm not sure I'm going to have time to go through all of this, but I will try to tell you a bit about each of them. Now, the first way, well, the immediate way, I think the obvious way in which we should use dynamical binaries to test the theory is to understand, let me go back here, is to understand exactly what's causing this. Now, and what's causing this is the fact that your binary is evolving under gravitational radiation reaction. Okay, so your system is losing energy as gravitational waves. It needs to inspiral inwards. Therefore, the velocities of your system increase. So the amplitude of your gravitational wave signal increases, and so does the frequency. Okay, and we know roughly how to quantify this. Take a system that is bound by gravitational interaction, so binding energy that looks like this. Mu is reduced mass, m total mass, capital L, the orbital separation, and you might have other interactions. For example, the binary might be charged under the electromagnetic sector. But then it's losing energy. And at lowest order, you get the quadrupole formula. Okay, so capital omega is orbital frequency. Now, because the radiation emission causes the binary to evolve, the only thing you're left with is to equate the time derivative of this guy to the time derivative of the binding energy, right? So this is the balance law. This is how you get how the orbital frequency, or if you wish, the orbital separation evolves as a function of time. Of course, if you have other emission channels, like a dipolar channel, if these guys are charged, then you have other contributions. But conceptually, this is how it goes. Now, because you know how the system evolves, then you can translate this into how your gravitational wave amplitude h looks like. And in a stationary phase approximation, well, it looks like it has a phase, capital psi, that evolves as a function of frequency. So frequency for me is this small f, and x is basically f to the 2/3. It's a measure of the velocity of your system, okay? Now, the dominant term is a frequency to the -5/3. This is pure general relativity, but you might have a dipolar term. This comes at -1 Pn order. I'm going to call this Pn orders depending on the exponent of this variable x, okay? For example, if Newton's constant varies as a function of time, at least in some theories, this comes as a -4 Pn term. Dynamical friction, the drag that the environment exerts on your binary, comes at -5.5 Pn order for fluids. Okay? If the graviton has a mass, then you'll get an extra correction at +1 Pn order, and so on and so forth. But you see, if you now use your signal to estimate these coefficients, you have a first robust way to test general relativity or the fact that you have black holes out there. And this is exactly what LIGO did in their first groundbreaking work. Okay, this is an example of what they did. They, instead of assuming GR, they parameterize each of these coefficients by some alpha. And they assume it's an unknown quantity, okay? So what I'm going to do is I freeze all of these parameters except one to be the GR prediction, and I see how much I can constrain this coefficient. And that's given here. This is the relative deviation with respect to what you expect in general relativity for the different Pn orders. Now, the first thing that you're going to notice is that you can constrain better the lowest Pn guys. So guys that come at -1, -2, -4 that LIGO did not show. The reason is obvious. Minus guys mean that they dominate at low frequencies, where the binary spends a lot of time before merger. So you can constrain well negative Pn orders, and you can constrain worse positive guys. Now, this is a theory agnostic.
Can I ask a question?
Yes, of course.
So basically, you're assuming here from the start that it's a quasi-circular motion.
That's correct.
And that, okay, and that's like how far back from the merger is it supposed to be a good assumption, or?
Oh, you can go back
like,
here. So you see, this is semi-major axis. So at A equals of order 1, which is where when they merge, this guy dropped to levels of 10 to -4, -5, -6. Okay, and especially what we are seeing now, we're only seeing the very last cycles in the life of a binary. So I think this is, at least for equal mass systems, a very reasonable assumption.
I see.
Yeah.
Okay, thanks.
Thank you for that. Now, however, I think we need to be a bit cautious about this way of doing things. If you give me your preferred theory, it's likely that it's going to affect all of these coefficients at once. So this way of constraining parameters by freezing all of them to be GR and just leaving one free has its limits. But also, sometimes it's oblivious to the most important content of the theory. Let me give you an example. If you take massive gravity theories, so a theory where the graviton is a massive guy, then you have an extra, well, actually you have extra degrees of freedom, extra polarizations that carry energy. Now, the traditional way of testing if the graviton is massive or not is by looking for dispersion effects as the wave travels. And this is a +1 Pn effect, okay? Now, it so happens that massive gravity introduces an extra dipolar mode that by far dominates emission at low frequencies. And so the best way of actually constraining massive gravity is not by looking at these type of constructions, but actually working out the radiative degrees of freedom of the theory. And you can show that you can almost rule out massive gravity just from the dipolar term of the theory, okay? So this is just my word of caution. Now, this is what we've done up to now is to test the theory using the low velocity regime, where the guys are well separated, they're doing a low frequency orbital motion. But you can do almost the opposite. You can go and look at the stage where they actually merged, okay? Now, the signal looks like this. The black holes merge roughly at this point. Then what you see afterwards is the final distorted object relaxing to the final state, which, according to general relativity, is a Kerr black hole. Now, at late times, a Kerr black hole is stationary, it's not emitting anything, so you must have a silent spacetime. So if you imagine going backwards in time, what you're going to find is a slightly disturbed Kerr black hole after merger, right? So this gives you kind of a handle on how to study this problem. You can expand the field equations around a single disturbed or fluctuated Kerr spacetime. And when you do this, you're going to find that your system of metric fluctuations, actually curvature fluctuations, is described by a single partial differential equation, second order partial differential equation that looks like this guy that I wrote here. There's a non-trivial effective potential V and a source term that roughly tells you the initial conditions of your problem or what exactly is causing the perturbation to the black hole. For example, S, the source term S could describe my hand waving close to a black hole spacetime, or it could describe the initial conditions that the merger of those two black holes left behind, okay? Now, because it's a linear system, it's a linear equation, we can use traditional tools, for example, doing a Fourier transform. And if you do this, you end up with the resolvent of your equation, a very simple looking operator, okay? And the first thing you're going to do in the frequency domain is to look for the characteristic frequencies for which your system satisfies the correct boundary conditions. And correct boundary conditions are basically that you have regular solutions everywhere and outgoing modes at large distances. It's really exactly the way you would look at and study a string with fixed ends or the hydrogen atom in quantum mechanics and so on. Now, the difference is a black hole spacetime is by its very nature a non-conservative system, right? Because you're losing energy to your boundaries, to the event horizon and to null infinity. And this means that your characteristic frequencies, omega, actually lie in the complex plane, okay? And I wrote this down as having an imaginary component and a real component. So these relate to the time scale of your fluctuation, because you see, if omega is complex, the imaginary part will basically make your fluctuation damp out, and the real part will make it oscillate, okay? So the upshot of all of this is that at late times, your gravitational wave signal H, okay, should be a superposition of exponentially damped sinusoids, where we know this time scale tau and frequency f to 20 decimal places or more from perturbation theory. We know what we're looking for. Okay, if there's questions here, please do them now. Okay, now you see there's a countable infinity of solutions. Just think about the hydrogen atom. It's really the same scheme. And we usually order them by the one with the longest time scale tau. That's the fluctuation that's going to dominate your signal. Okay, what you're going to see at late times is the eigenfrequency with the longest lifetime. And I wrote it down here for a non-spinning black hole of 10 solar masses. These are the numbers we're talking about. For a 10 solar mass black hole, the frequency is of order 1 kilohertz, and the lifetime is of order 0.5 milliseconds. Now, it's always useful to remind ourselves that a 10 solar mass black hole has the size of Boston or so, okay? So I think it's impressive to see that an object the size of Boston relaxes on a timescale of a fraction of a millisecond. And of course, the reason is the relaxation is traveling at the speed of light, right? Very good. Now, the idea is really simple. We know these frequencies to an extreme precision, so we just need to fit our data to these numbers and see what we recover, okay? Now, if you think about doing this, the first immediate problem you're going to face is when exactly does this so-called ringdown start? Does it start here? Does it start at the peak of your waveform? Does it start here? And we do not know. And there's a reason why we don't know, because the problem is not well defined. If you look at wave propagation in curved spacetime, so at the structure of your Green's function, you're going to see that a detector placed somewhere here, okay, will see waves generated by a source, this source, a planet close to a black hole, and some of those waves are a prompt emission, so they travel directly from source to observer, but some of them actually just got bent by the black hole. They circle the black hole once or multiple times before reaching the detector. And some others actually backscatter off the space-time curvature at large spatial distances. This is a branch cut actually in your Green's function. So there is no ring-down start time, okay? There's no well-defined notion of a start time. So the best you can do, well, is try to see what happens when you change the start time, when you slide your start time across the waveform. This is exactly what LIGO did. Okay, so black solid line here is the 90% posterior distribution when you look at all of the signal. You take your best fitting numerical waveform and you calculate mass and spin of the final black hole. And then you show the decay time and the frequency, okay? So you have an estimate for these guys. Now you fit this signal starting 1 millisecond after the peak, 3 milliseconds, 5 milliseconds, and so on and so forth. And you realize that if you start fitting too early, so if you start fitting at the peak of this waveform, you're still getting contributions from the early part, from the inspiral part. It's not a good approximation. So this is off the final state. But as you go later in time, you see that all of this is consistent. Okay, I think it's a fantastic, it looks awful. It looks awful because the error is huge. But you have to remember that the signal to noise ratio in this signal, in the ring down signal, is 7. It's marginally detectable, okay? So I think for the first test of general relativity using gravitational waves from black holes, this is a marvelous plot. It's a marvelous test. Now, this is the things we'll be doing 10 years from now. 10 years from now, you're going to be measuring ring down, the relaxation of black holes, with signal to noise ratios of 40. And with signal to noise ratios of 40, this is how the 90% distribution of the quadrupolar term looks like. Again, timescale tau on the y-axis, frequency on the x-axis. In fact, it's so good that you're going to be measuring more than one mode. You're also going to be measuring the octupolar mode. Okay? It's a signal to noise ratio of 40. Lisa will be measuring ring down with signal to noise ratios of 1,000. I can't even plot that here. The error is going to be so tiny. So these will be fully fledged spectroscopy tests of general relativity and of black hole physics. So I think it's a wonderful thing that we have 15 years from now. Now, I told you that we're linearizing the theory. Okay, so let me now tell you a few words about the things we thought we were losing or not. When you linearize the theory, of course, you lose information. You lose information about nonlinearities, for example. Okay? And it was thought, when people were looking at this waveform, this is a numerical relativity waveform. It was thought that the signal is strangely smooth and it looks so linear. The ring down, we looked at the ring down, and it seems that it only contains linear stuff. Okay, even using numerical relativity waveforms. And I think there were several explanations for a few decades, if you wish, about why this is so. Because the light ring is filtering the high frequency component and the nonlinearities and so on and so forth. This is wrong, okay? This is wrong. You can search for nonlinearities in the following way. If you now extend your fluctuation formalism to second order, you will realize, so instead, let me go back here. What we were doing was linearizing the field equations, and the first order quantity is this guy psi. If you now take the formalism to second order, you'll see that your fluctuations, second order, so psi 2, will be described by a similar partial differential equation that is sourced by the first order guys. Okay? So if you have nonlinearities in ringdown, then there should be extra frequencies. So imagine that psi 1 is an exponentially damped sinusoid. The square of that guy will give you terms that roughly are twice the frequency of the linear problem, okay? If they exist. So we search for them, okay? We search for them in quasi-circular mergers, but also in head-on guys. The head-on collisions is a very simple and clean problem because you can tune the center of mass energy, okay? And when we did this, we noticed that there's an extra mode in the L equals 4 angular dependence that comes from a combination of the quadrupolar linear term. So we call this a 200 cross 200 mode. It's a nonlinear contribution, okay? And I'm showing you here the amplitude of this nonlinear mode as a function of the amplitude that you find in the waveform of the linear mode, okay? And how do we change the amplitude of the linear mode? Well, we just start varying the center of mass energy of the collision. We collide two black holes, we change the velocity of the center, the velocity at which they collide, so we put more energy into the relaxation. And it's a beautiful quadratic dependence. The slope of this guy, so the amplitude of this nonlinear mode goes like the square, roughly 1.9, it's the same. The square of the amplitude of the linear mode, exactly as you expect for this type of frame, of perturbative framework, okay? It's a beautiful thing. In fact, I think there's mysteries associated to this. There's a nice paper conjecturing or showing that you get exactly the same amplitudes of nonlinear modes from the Kerr CFT perspective. I think there's a lot to be said. The agreement seems to be too good to be pure coincidence, but I think a lot more needs to be explored in this aspect. Now, Shahar, do you have a question?
Yeah, I do. I wanted to ask, so this is an L equals 4 mode, which is generated by a nonlinear interaction of two L equals 2.
That's
right?
correct. So you go at
Okay.
the angular dependence. So you take the Y, the spherical harmonic L equals 4, and you see which modes are there. And we find that besides the linear L equals 4 mode, the frequency, we also find an extra guy, which I am calling the square, a contribution that comes from the square of an L equals 2 mode. Because if you square an L equals 2 spherical harmonic, among others, you're going to get an L equals 4, right?
Right.
Yeah.
Okay, so it is also generated linearly, but you're subtracting that and you have an extra contribution.
That's correct.
Okay. I
Yeah.
see. Okay, thanks.
And the amplitude of this guy with respect, well, it's here, right? It can be up to 10% of the linear mode, for example, for this type of simulations.
Okay, thanks.
Now, the other question you might ask is, well, we're doing all of this in vacuum, but the universe is anything but vacuum. I mean, we exist, so obviously it can't be vacuum. So what happens when you change your problem into something that has some matter? It's a very complex problem, this one, okay? So I'm not going to do that. What I'm going to do is so because the space-time structure is encoded in the effective potential governing your partial differential equation, what I'm going to do is I'm going to change very slightly that effective potential and see what I get, okay? So for example, the effective potential in vacuum looks like this purple curve. It's peaked close to the black hole. In fact, it's peaked close to the light ring of the black hole, and then it quickly goes to 0. What I'm going to do is I'll add a bump far away from the black hole, a very tiny bump that's supposed to mimic a star or the content of a galaxy or another binary far away. Okay? There's no, I can't give you a direct meaning. You would have to work out the equations when you put some matter there. But the idea is to see how do we change the spectrum of black holes if we start tweaking this effective potential, okay? So it looks like this. There's a bump of height epsilon, a distance r naught away from the black hole, and with a width sigma, okay? Now, the extraordinary thing, I mean, you'd expect that nothing changes when epsilon goes to 0. That's basically what we expect, okay? But when you start working out the spectrum of these characteristic frequencies, you'll be surprised, okay? This is what you get. So here, it's the imaginary component of the frequency on the y-axis, real axis, the real part. And I'm going to change the distance at which the bump is located. Okay, the height of the bump is 10 to minus 6. It's really a small guy. Shouldn't make any difference at all. Okay, but I'm going to track the frequency as I change the location of the bump. So I start at 0 here. Okay, and now I'm going to change the location of the bump. And you see that your characteristic frequency changes by an arbitrary amount. Even though all you have is a small bump far away from your black hole, the characteristic frequencies change by how much you want, okay? Actually, this is a big problem. It could be a big problem. Because it could be telling us that LIGO is not measuring anything meaningful, right? If a grain of dust affects the predictions for the relaxation of a black hole, it means we can't trust anything at all. Now, this problem actually is known in quantum mechanics. It's called the elephant and the flea problem, and it's been known for some decades, that you can change the spectrum by an arbitrary amount of, with an arbitrarily small fluctuation, okay? It seems the same happens in black hole physics, okay? And there's no way around this. However, the time domain response, it's interesting. Let me show you what happens when you actually follow the time evolution of some initial disturbance around the black hole. So here I'm showing you psi, the amplitude of the gravitational wave, as a function of time, okay, for bumps that are located at a distance of 10 or 30 away from the black hole. The amplitude of this bump is, well, it varies. It's 0 for the black line, so it's a vacuum guy, or 10 to minus 3 or so for the smallest epsilon. The lower panels show you the difference in the response between the guy with the bump and the vacuum case, okay? And what you find, it's interesting, it's a lesson that we learned. What you find is that at early times, all of these responses are the same. So the green line overlaps with the blue, it overlaps with the orange, it overlaps with the black for all of these guys, okay? But at late times, well, at late times what happens? Let me go back to this plot over here. You generate the response when you perturb the light ring. That gives you a burst of radiation. Now, this burst of radiation is high frequency, so it crosses the space-time, it reaches the detector, and it's fine. But a small fraction of it is reflected by the bump. And you see, there's a cavity there. It's a cavity between the light ring and this bump that's filtering low-frequency components. And it's the low-frequency component that's going to dictate the late-time behavior. And the late-time behavior is actually what your spectrum is telling you. Your characteristic frequencies only tell you about the late-time response. They don't tell you about transients, okay? So the morale of all of this is be very careful when you calculate characteristic frequencies. They are not telling you the full story, okay? There's an elephant and there's a flea, but the elephant is only scratching at very late times. It's not bothered by the flea early on. Very good. But now let me go to the real thing. How can we then use black holes to test the environment, okay? There's different ways. I think this is a field that's emerging in the last 2-3 years because there's a lot to understand at the theory level. Now, when you place a black hole binary in some environment, it's going to accrete matter, it's going to be gravitationally pulled by the environment, and all of this is going to change the way the Inspiral proceeds, okay? If you do a very naive estimate, the dominant effect is the gravitational drag that comes at minus 5.5 p-n term. So you can use this to estimate the sensitivity of your detector to the environment. So we've done this, we and several other people, a few years ago, okay? And this is how it looks like. Gravitational wave detectors working now, like LIGO, can discriminate environments whose density is of the order of water, okay? This is for LIGO. This is how we do it, right? We track the Inspiral, and if it goes according to what we predict in vacuum, then it rules out environments whose density goes like the water. So I'm measuring y-axis in units of density of water. But detectors like LISA, if we understand well the evolution of a binary inside an environment, is able to constrain environmental densities of order 10 to minus 9 or even 10 to minus 12 that of water. You're doing accretion disk physics now. It's a fantastic thing. Or even dark matter physics if you have high enough densities, okay? But I'm going to finish my my discussion on black holes as tools, not with fluids or dark matter that we know is there, but with new fundamental fields. Fields for which the density, the initial density can even be 0, okay? And let me show you how this works, okay? Now, the reason to do this, of course, I don't think I need to explain, is because we still have no idea on what the nature of dark matter is, okay? It could be either primordial small black holes, but it could also be new degrees of freedom. And the way we have to constrain these new degrees of freedom is to assume they couple to the standard model. This is a typical exclusion plot that we do with known experiments, with ongoing experiments. So you plot the coupling to the standard model on the y-axis and the mass of your degree of freedom on the x-axis. If the coupling is large enough, it's talking to the standard model well, then you're able to constrain that field, that degree of freedom, okay? However, if the coupling is very small, you're screwed if you're looking for it in the electromagnetic band, okay? Now, I'd like to discuss for 5 minutes, if I have them, a mechanism that doesn't even require that you talk to the standard model. It only uses the equivalence principle because everything falls in the same way. I'm going to show you now that even with 0 coupling, you should be able to do stuff, to look for new fundamental fields, okay? And these are well motivated. The original axion term to explain the smallness of the neutron dipolar moment looks something like this, right? You invoke the existence of a pseudoscalar psi that couples to the Maxwell sector in something like this, okay? Now, if you have a theory like this and you have a spinning black hole, what you get is a condensation of psi around the black hole. And the idea is really simple, and it works as in the Earth-Moon system, okay? Take the Earth-Moon system here. This is called superradiance, or in planetary physics, it's called tidal acceleration. And the idea is simple. You have an object, the Earth, going around the moon with a very low frequency, but the Earth is spinning around its axis every 24 hours. So it's spinning very fast, okay? Now, there's oceans on the surface of the Earth, and because the Earth is spinning very fast, it wants to spin, it wants to drag the oceans with it, okay? So the friction between the crust and the ocean creates a very small tidal angle with the Earth-Moon axis, Okay. Now, but because of this friction, you're going to have transfer of energy between the Earth and the Moon. Why? Because you need to conserve angular momentum. Okay, but friction wants to increase the day. It wants to decrease the period of the Earth, right? But to conserve angular momentum, the only way you can do this, you can achieve this, is by pushing the Moon farther away. And this has been measured with lunar laser ranging. So the Moon is getting farther away from us at the pace of 1 centimeter or so per year. So you see, you have an exchange of energy between the spinning system and the Moon. The same happens for any spinning system. So if you have a spinning black hole and you throw it a slowly spinning Moon, so to speak, this is a low frequency field. This field is going to extract energy away from your spinning black hole. Okay? Now, if your field were massless, that would be the end of it. You extract a bit of energy and end of story. But if your field is massive, well, it needs to fall back on the spinning black hole. But it's going to be amplified there. Okay, it's going to be amplified, it tries to escape, but it's going to fall back again. So this gives you an exponential energy extraction mechanism that we call a superradiance instability. Okay? Timescales are really small. For an astrophysical black hole of 10 to the 6th solar mass and a field of 10 to the minus 16 electron volt, we're talking about 100 seconds or so. Okay? Now, you see, you need to fine-tune the fundamental mass of your bosonic field. But the good news is black holes in the universe come across a wide range of masses. So there's always going to be a black hole for which this is tuned to have a small time scale. Okay? So you can use this to search for new degrees of freedom. You just look at black holes out there, you measure mass and spin, and this is going to exclude your fundamental field mass. For example, look at the blue line in this plot. The blue, above this blue line, any black hole should be unstable on timescales of 10,000 years. We should not be seeing black holes here. But yet, these are measurements, okay? So these red crosses here are excluding boson masses of the order of 10 to the minus 18 electron volt. In fact, the particle data group now is using superradiant measurements as their state-of-the-art exclusion for the graviton mass, for example. Okay? And the idea is always the same. You look out there, see spinning black holes. This must mean there isn't a boson mass in this range. Okay? But you can also do it with gravitational wave emission because what the system does is to condense a cloud of bosons around your spinning black hole. It's non-axisymmetric, so it's releasing a huge amount of gravitational radiation. We should be seeing it. And the fact that we don't see it is also going to exclude the boson. Okay? This is one example. LIGO, for example, this is the sensitivity curve for a stochastic background of gravitational waves by LIGO in run 01 to run 05. Okay? The non-observation of a stochastic background is going to exclude bosons in the range of roughly 10 to the minus 12 electron volt. So it's a beautiful new era where we can use different detectors to exclude fundamental fields across almost 10 orders of magnitude. LISA will be excluding bosons of mass 10 to the minus 18 or 10 to the minus 19 electron volt. It's a beautiful thing. And if you go to my lecture notes, you will find the different type of observations that are able to exclude boson masses in a really wide range of masses. So I'll stop here, but let me just say, sorry?
Is there anything interesting you can say about fermions that don't have superradiance? Any other effect?
So there is, yes, that's actually, that's I think an ongoing project by two different groups. Now, these constraints assume that there's no coupling at all to the standard model. So you just have your axion or your scalar field, it's producing a cloud, and the cloud is spinning the black hole down and emitting gravitational waves. If you now talk to the standard model, for example, here, I had a few slides on this, so I'm happy you asked. So for example, look at this coupling over here, right? Now you couple your axion to the Maxwell sector, that's going to give you different things. For example, it's going to give you birefringence of your photons. The plane of polarization is going to oscillate. And this was used by Ifan and other people to set constraints on the amount of axion that you have around the black hole. But it's also going to do a different thing. So when you start talking to the standard model, instead of channeling the rotational energy to the black hole, you could instead giving it a burst of photons. And this is what we saw a few years ago, right? You start growing the cloud. Let me show you here. You throw a small fluctuation of vector field, so some photons, and you see that you get a burst of photons. You decrease the amplitude of your cloud, and then you need to wait a few thousand years until you grow the cloud again. You get another burst of radiation, and so on and so forth. Now, your question was about fermions. Fermions don't have superradiance, so they would not condense around the black hole. But if you have a coupling between your scalar or pseudoscalar and your fermion, then you might get bursts of fermions as well. To my knowledge, this was not worked out. This is something actually we are thinking here on how to use this to constrain things, but this has not been worked out in any detail at all.
Okay, thanks.
Okay. So I think this is a wonderful excuse to finish now. I think it's really a fantastic era ahead of us. There's a tremendous amount of new physics that we can explore and that we have instruments to look for. Well, I think we need a bit of imagination and ideas in the field, but it's progressing wonderfully. So we are in a wonderful situation. So thank you so much.
All right, let's all thank Vitor for a fantastic, very clear talk. We have plenty of time for questions, so just unmute yourself and ask away.
So regarding the elephant and the flea problem with the quasi-normal modes, so is this instability kind of telling us that maybe the quasi-normal mode frequencies are not good physical quantities to think about, or can we somehow define them differently so they would be not?
That's a golden question,
stable,
Shahad. Yeah, I think that's really a golden question. What they're telling us is, yes, it's a happy coincidence that for black holes, the quasi-normal modes also correspond to the relaxation of the light ring. In general, they don't. But the relaxation of the light ring is actually what controls the early time response, the dominant component of the signal. And for most systems, it happens that it's not in the spectrum, right? And so there should be a different measure. I believe there must be a different tool, a spectral tool, that tells you about the light ring. But me and other people, I think, have been looking for this for 5 years now, and it seems we're not smart enough for that yet. So but there must be a different way of telling the problem. There you go. It's not in the spectrum, but it's in a quasi-spectrum, if you wish. Yeah. But the lesson also is, even though you're perturbing the spectrum by an arbitrarily large amount, the time domain response that our current detectors can probe is still the same. So that's fine.
Thanks.
But isn't it, I thought that the sort of the fundamental mode actually was pretty stable even under these perturbations, and that it was
It
the
is not.
overtones that
No, it is
really.
not. Yeah, the fundamental mode is exactly what I'm showing here, and that's totally disturbed. So it was, maybe you're referring to the pseudo-spectral analysis, but there, what they studied was a high frequency fluctuation. And for high frequency fluctuations, it seems that the fundamental mode is stable, but we are not doing a high frequency fluctuation. We are doing actually a small, if you wish, a small wave number fluctuation, because we're placing a bump very far away.
Yes. Do you have any more questions?
Yeah, I'll ask a quick one. Is it understood, Vitor, at some heuristic level or even in the literature, if a perturbation, if you have like a point source that passes through the photon shell, so for a Kerr black hole, which is not just one radius, but many radii, is there some sense in which if a source is at some radius in the photon shell, it preferentially excites one of the quasi-normal modes associated with that radius in the photon shell? Is that something you've looked into?
No, I don't think even heuristically we know this. I don't think this was looked at in any detail by anyone. That's a question that came up a few months ago. So I think we did some search of that and we did some thinking, and this is not done to any detail. Yeah, so that would be welcome. There's insights on that as well.
Okay, thank you. That's very valuable. Thanks.
Okay, well, let's thank Vitor again for a great talk.
Thank you. It's my pleasure, really.
Yeah, lots to think about.